Okay, like I said, I'm trying to break this into sections here. So here's another thing that we can tackle, and that is what if I want to essentially change the solubility of things, either decrease them or increase them. For example, make a particular compound more insoluble or a particular compound more soluble, all right? Let's see how far we can get. We're not able to cover everything here, but we'll try our best, all right? So let's start out with selectively making a compound less soluble, all right? So let's come back here to our PowerPoint, and we did this problem, and now we're gonna talk about, again, the common ion effect. Remember that? We talked about it when we built buffers. We said the presence of an ion that is held in common between a equilibrium that we're interested in and something else that we add in there is going to typically suppress the direction of the, in that case, it was the ionization, but in this case, it's going to be the solubility. Okay, that's a lot of words. Let's look at the slides here. So the presence of a common ion essentially is going to decrease the solubility of the salt or the compound, right? So let's start out by saying, what would be the molar solubility of silver bromide in pure water or in 0.0010 molar NaBr? All right, let's start out with silver bromide. Remember, we had already found out that for silver bromide, dissociating into its ions, the Ksp was 5.4 times 10 to the minus 13. And because, sorry, because Ksp is the product of the ion concentrations, and the ion concentrations are given by the molar solubility, or S. This should be S squared, right? And therefore, S should be the square root of Ksp, which is 7.3 times 10 to the minus 7. Okay, let me give you a few seconds in case you kind of got lost in there. Remember, in these equilibria, S is the moles per liter of dissolved compound, and where the compound simply breaks down into, you know, a 1-to-1 ratio of cation and anion, each one of those will have S moles per liter in solution. Therefore, S squared will be the value of Ksp. Now, let's go looking at a different situation. Let's say now I put in sodium bromide, a strong electrolyte, in other words, a completely soluble compound that will totally dissociate into sodium and bromide ions. So if I started with 0.0010 molar sodium bromide, that means that I have now that same concentration in sodium and in bromide ions, right? So now I have bromide ions in this amount here. Now, I'm going to look at my equilibrium again. So the difference now is that I no longer start with 0 silver and 0 bromide. I start out with 0 silver, but the presence of the bromide ion in here, okay, the presence of the bromide ion here should cause this equilibrium to shift towards the left, right? That's Le Chatelier. If the right side of the equation is a little heavier, the equilibrium wants to shift back towards the left, which is the undissolved compound. So in this case, what you have is S moles per liter of silver and 0.001 molar of bromide plus S. But remember, molar solubility is very small. So we could say that's probably negligible here, and we're going to leave it there. And so in order to achieve the value of Ksp, that would be 0.0010 times S. So I'm going to solve for S. We already have the value of Ksp over here, right? So we're going to solve for S here, and we get 5.4 times 10 to the negative 10. So notice that if I put the silver bromide in water, 7.3 times 10 to the negative 7 moles per liter of compound dissolved. But if I have it in a solution that has bromide ions in it, it drops to 5.4 times 10 to the negative 10. Again, the presence of the bromide ion already in there drives the equilibrium back towards the undissolved salt or compound, which means the solubility decreases. All right? Okay, let me know if there's any questions about that. So again, we first started out by discussing KSP and how to convert between KSP and solubility and stuff like that. Then we talked about how to use these KSP values to either predict precipitation reactions or predict the order in which precipitation is going to happen. Now we're looking at how to use these equilibria to see how we can alter the solubility profile. In this case, we just talked about decreasing the solubility of a particular compound. Let's look now at some ways that we can use to increase the solubility of compounds. And one of the preferred ones is for compounds that involve, for example, the hydroxide ion or anything like that, we can alter the solubility by changing the pH of the solution. We can do it that way, all right? So, for example, this is the same idea. The common ion decreases solubility. So what's going to happen is if I have an insoluble base, practice tells me that they will dissolve easily in acidic solutions. For example, the hard water deposits you might get in your sink or your bathtub, which comes from calcium carbonate, will typically dissolve in vinegar, which is acidic. Insoluble acids will typically dissolve in basic solutions. So some of those insoluble acids, I don't know, like benzoic and stuff like that, a lot of organic acids will dissolve with ammonia, right? So let's look at an example. Here is magnesium hydroxide, a slightly insoluble, slightly soluble compound that dissociates into magnesium and hydroxide ions. Okay, so let's play with this first of all. Okay, KSP would be the concentration of magnesium times the square, be careful, right? Don't forget those stoichiometric coefficients there, the square of the hydroxide ion concentration. And let's say KSP is 2.1 times 10 to the negative 11. Now, if we were to look at solubility here, we would say that, again, at equilibrium, each one of the ions has a proportion of the molar solubility of the compound, S. So this would be magnesium S, hydroxide is 2S squared. Remember, it's not 2 times S squared, it's 2S, the whole thing squared, because that's the molarity here. So this would be S. Oops, sorry. Let me erase that. So this would be S, and this would be 2S. All right. So that means it's 4S cubed. And so if I want to solve that out, I divide by 4 and I take the cubic root of it, and I get that my molar solubility is 1.7 times 10 to the negative 4 molar. If I wanted to calculate molarities, that'd be fine. I can do that. I can say, well, the OH concentration would be 2 times the molarity here, and that would be 3.4 times 10 to the negative 4, which means that the POH will be minus the logarithm of that, and therefore the pH will be 14 minus that, 10.53. So it's telling me that a saturated solution of magnesium hydroxide should have an alkaline or basic pH, because even though it is insoluble, there are sufficient hydroxide ions being put into solution to give me a basic pH. All right, everybody with me? Let me know if you're lost or if you have any questions. Okay, so let's do this. Let's ask, what happens if I change the pH of the solution? For example, what if I add some acid and I make the pH less than 10.53? So what that means is, what I'm doing in effect is, if I'm lowering the pH, right, that means that I'm lowering the hydroxide ion concentration. I'm less basic, right? Now, if you look at the equation up there, remember, this is Le Chatelier. I am making the right side of that equation lighter. So by removing hydroxide ions, I am going to drive this equilibrium to the right, which means I am dissolving additional magnesium hydroxide. Or, in other words, I am increasing the solubility of magnesium hydroxide. Got it? Cool. So if I have this type of compound here, right, and I add water and it won't come off because it's not as soluble, some acidity will help. For example, vinegar or maybe boric acid, something like that. I forget which one to use preferably here. I use vinegar most of the time. Okay, so what happens if I increase the pH? In other words, let's say I make it more basic. Let's say I add, I don't know, NaOH or something like that. Anything that you add that is basic means you're increasing the concentration of hydroxide ions, right? So looking at the equilibrium there, you can see that if I add hydroxide ions, this equilibrium is going to shift to the left. In other words, to the undissolved compound. In other words, I would be decreasing the solubility of magnesium hydroxide. All right, so let's wrap it up here by going through a set of exercises here. Again, remember, the idea here is that if the compound in question here has an ion that is susceptible to changes in pH, then I should be able to alter the solubility of the compound by changing the pH. However, I need to decide if what I need to do is, increase the pH or decrease the pH. In other words, do I need to add acid or do I need to add base, right? So let's look at these exercises here. And I think you have this slide in your handout. We're going to look at these 4 compounds: calcium hydroxide, magnesium phosphate, lead 2 bromide, and benzoic acid. All right, these are the compounds we're looking at. Will increasing the acidity also increase the solubility of these guys? Well, do you guys want to do it on paper here? Let's do it on paper here. Let's do it here. Okay, calcium hydroxide. Let's look at the equilibrium. Calcium hydroxide gives me calcium ions plus hydroxide ions. There's 2 of those. Okay, so let's say that I add acid. If I add acid, what happens to the hydroxide ion concentration? Does it increase or does it decrease? Decreases, right? So that means, according to the Le Chatelier principle, what's going to happen? If this is decreasing, equilibrium shifts to the right, right? In other words, towards the dissolved form. And that means that for calcium hydroxide, yes, increasing acidity is going to increase the solubility. Okay, let's look at magnesium phosphate. This is 3 and 2. So this is going to give me 3 units of magnesium and 2 of phosphate. Okay, so this one might not be as obvious. But I had to think, do I have anybody here who is either like a base or something like that? Is phosphate ion the conjugate of something? Yes. Phosphate ion is the conjugate of hydrogen phosphate. So if I increase this, right, that's going to pull the phosphate ions from that equilibrium, and that's going to cause by Le Chatelier this equilibrium to push towards the right. In other words, more of the magnesium phosphate is going to dissolve. Notice the trick here. You had to be able to recognize phosphate ion as a potential conjugate base of a weak acid, right? Just remember, just an H of a difference, right? So we would say therefore that for magnesium phosphate, yes, putting acid would help dissolve it. All right, what about lead to bromide? That would dissolve into lead 2 ions and bromide ions. So bromide is negatively charged, so it would be the conjugate base of what? Again, add an H to it. That's right, hydrobromic acid. Strong acid. In other words, the bromide ion is not going to do what phosphate does or what hydroxide ions do in the presence of acid. They're not going to go back towards hydrogen bromide, so hydrobromic acid. So that means that for this compound, the answer is no. You're not going to get any help from acid. All right. What do you guys think about benzoic acid? If it's an acid, will increasing acidity increase its solubility? I mean, if you guys want, we can work on it, right? Let's see if I have running out of room here. Oops. You know what, guys? Let me get this thing out of here. Sorry, guys. I'm having some space issues here. Come on, man. There you go. Benzoic acid. What do we say it was? C6. It's actually not 6,6. It's, well, they write it that way. Okay, so that's fine. C6H5COOH. And we're trying to make it into C5, C6, C6H5COO minus. Hydrogen ions because it is an acid. So if I increase the acid, which way does this equilibrium go? No, it goes this way, right? Because you increase something on the right side, the equilibrium shifts towards the left, which is the actual undissolved compound. So for benzoic acid, in other words, you're not going to get any help by adding more acid to that mixture. How would you do it then? What would you add? Base, right? You could add a base to cause this equilibrium that we just drew here, make it go instead of to the left, add base that removes hydrogen ions and therefore draws this equilibrium back towards the right, which is the dissolved form of the benzoic acid, right? So that is how you deal with these things, all right? All right. Okay, let me come back here, see if there are any questions. We're running out of time. So I gotta see what we have next. Yeah, we have one more problem here, but tell you what I'm gonna do is I am probably gonna post this one. It's a little involved and I don't wanna be in a time crunch here. So our next question that we have, let me go back to our PowerPoint here, would have been this. So we had, essentially we said that in this case, the calcium hydroxide will respond, will increase solubility if I add acid. The magnesium phosphate also, but the lead 2 bromide and the benzoic acid won't. Okay, the next problem we have here is very interesting, but I think it merits a little more time and we're kind of out of time. So I have several possibilities here. One of them is, I could simply do the rest of this presentation on a recording. Or if you guys want, we can take the first few minutes of the session on Tuesday before our review to go over this and finish this topic out. I would feel better with that because I'm not sure that when I simply record things, nobody's in the audience. I don't get the feedback. So if I make a mistake, I'm not gonna find out about it until later. So let me know if there's any questions about this stuff we just discussed. Okay, so to wrap it up, what we used to call insoluble compounds in Chem 1A, we find now that these are actually compounds that establish an equilibrium when they form a saturated solution. The equilibrium is described by a constant called Ksp, and based on the value of Ksp, we can do several manipulations. For example, we can calculate what is the solubility of the compound in terms of grams per liter, or in terms of moles per liter, or vice versa. Given those values, we can calculate Ksp, right? We can then apply the concept in several ways. For example, we can do things like, for example, calculate if I combine two solutions and they result in these molarities, will there be a precipitation or not? Or I can ask the question, if I have a combination of different ions, can I predict in what order they will precipitate, right? And the other thing that we did was here, we can alter solubility. We can either decrease solubility by adding a common ion, or we can increase solubility by manipulating the pH of the environment if the ions produced by the solubility equilibrium are susceptible to pH, all right? Somebody wanted slide 39. Slide 39. I just don't keep track of the numbers. So I don't know which one that was. Ooh, that was a long time ago. Let's see if I can go back there.
Mine are numbered differently, so it might not be 30.
Yeah, I know.
It was the selectively decreasing solubility, the first one we did.
The one with the magnesium hydroxide?
Yes. So no,
This one?
Yes. Thank you.
All right. Let's put it there for a little bit so everybody can see it. Okay, let me know.
I'm good, thank you.
All righty. Cool. Any other questions? We still have a couple of minutes. So what we're gonna do is we'll take a break here, right? And if you want, we will restart like at 7:10 or so. And we're gonna go over that activity that's in your Canvas page. It's the guided activity on, it's another activity on buffers, but there's also an activity where you calculate the Ka of a weak acid by 4 different methods. I think we've only used one in class before, but we have 3 other methods to do it. Okay, any questions? No? Okay, well, I'm gonna basically